And so we will start off with a talk by Roxane Ligi from the Observatoire de la Côte d'Azur. I hope I didn't butcher that with my high school French. And Roxane will tell us about a topic that we've heard about, or hinted at a couple of times already during the workshop, and that is interferometry and its connection to Gaia. So take it away, Roxane.
Thank you, Dan. So hello, everybody. I'm very glad to be with you, not you personally, but with you anyway. And I would like to thank the SOC for letting me speak about Gaia and interferometric observation in the context of exoplanetary science. So let's start with a diagram that you probably know, everyone, or at least have seen at least once. It's a diagram presenting the mass of exoplanets as a function of their semi-major axis. Today we have discovered nearly 5,000 exoplanets with a very wide range of methods. So there is a transit method where the discoveries are showed with the blue points here. There is also the radial velocity measurements that we heard about yesterday in orange, and microlensing in red, and also the planets that were detected with direct imaging here far away from the star in green. So we can see different features in this diagram. First, there is a lack of continuum in the exoplanets here in this part. We can also notice here a gap, which is called the Photon Gap or evaporation valley, because it separates two kind of telluric planets, the super Earths and the mini Neptune planets. And we can also see here a desert, which can be an observational gap where we cannot find any exoplanets. So having detected so many exoplanets bring all the problematics that are related to them. For example, what is the nature of exoplanets? How are they made of? What is their size? What does it correspond to? How did they form? Did they form far away or close to their parent star? Did they migrate? And of course, it brings the question of habitability, which is, could we find life on one of these exoplanets? And of course, is our solar system unique? Could we find other stellar systems where there is the same kind of exoplanet, and in particular another Earth? So with all the exoplanets that we have detected, we are getting closer to Earth-like planets, but we still haven't really detected a twin of the Earth at the same distance from its star and around a star like our Sun. So all these methods bring different kind of parameter. We already heard about the transit detection method, which is actually to measure the flux coming from the star. And when an exoplanet passes in front of the star, the luminosity, the flux that we receive diminishes. And actually this difference in flux is related to the ratio of the radius of the planetary to that of the star. So if you want to know the radius of the planet, you have to know the radius of the star. There is also the radial velocity measurements. So the same, we measure the reflex motion of the star when the planet is around it, spins around it. And actually what we measure is a ratio of the minimass of the exoplanet to that of the star. And if we know the inclination of the system, we have the ratio of the mass of the planet to that of the star. So once again, you have to know the mass of the star if you want to know the mass of the exoplanet. Another method is direct imaging. So I mostly show that because I really like this image of the system of HR 8799. So we can really see 4 planets orbiting around its star, which is hidden by the coronagraph. It's really amazing, but there are plenty of other systems where we detected with direct imaging. And actually, with this method, you can measure the spectrum of your planet, which is like this, for example, for the sphere direct imager. But to interpret these measurements, you need models, and in particular, you need to know the age of the star, as was mentioned by Ola this morning. So why do we need all of this? Well, the internal composition of exoplanets is inferred from the planetary interior models, which means that we cannot measure or directly what an exoplanet is made of. So we need all these parameters. These parameters feed the interior models of planets. For these models, we need both stellar and planetary parameters. And as a result, it will give us hints to understand formation and habitability of exoplanets. The problem is, of course, that like every model, it suffers from degeneracy. And for example, to give you an idea, if there is gas, if we found that there is an atmosphere or gas around on the planet, we will be able to know when it was formed, before or after it was too close to the star, so the atmosphere is irradiated. If there is ice of any element, we will know if it was made beyond the snow line or not. And of course, the metals and silicates tells us about the disk in which it was formed. So to infer the composition of these exoplanets, we use model. And for example, there is this model, which it's not a model, but the representation is what you call the Toblerone diagram, where for a fixed mass, you have a range of possible interiors as a function of the radius. And you already see here that if we have a precise knowledge of the radius, we will be able to infer a range of compositions of the exoplanets. If we don't know anything about the radius, all the compositions are plausible. And actually, it's usually said that we need 2 or 3% precision on the planetary radius to derive an internal structure of the planet. There are other parameters that depend on the stars, like the habitable zone. So in its very broad description, the habitable zone is the distance to the star for which, if there was water at the surface of a planet, it will be in a liquid state. And this depends on the effective temperature of the star, its luminosity, the distance between the star and the planet, many other parameters, but still we have to know the planet, the star for this. And with all the exoplanets we have detected so far, we can now start to make statistics about the populations of exoplanets. For example, we know since 2005 that there is a relation between the metallicity of the star and the number of stars that host exoplanets. So the more metallic it is, the more probable you will find planets around the star. And this is linked with the formation processes where you need elements in the disk to form exoplanets. So it has been also shown in many other ways in many studies, but we also know that there is a link between the number of planets and their radius, saying that if there are massive and with a big radius planets, they will have taken all the elements in the disk to be formed. So probably there will be less planets in the system. And for example, also the relation between the planet and the stellar mass has been highlighted by Johnson in 2010. So there are many studies. Those are just examples, but just to say that to study population of exoplanets, we also know to understand the parameters of the host stars. So I know that this has been said previously today by Ola and yesterday by Dan, but as we say, pedagogy is repetition. So I will say it once again because it's really important. Stellar parameters drive our knowledge of exoplanets. So there are direct and indirect methods that do not provide the same observables according to what they can measure directly. But in any case, we need the stellar parameters to derive the exoplanetary properties. And I would say that every parameter is important, but the basic parameter that you need is the mass, radius, and density. Either you will use them directly, either they will feed models to derive interior properties for planets, for example. And in this context, interferometry can help in many ways, and in particular by providing stellar parameters. But what is interferometry? So there are a few interferometers worldwide. I would say that the most important to me, because this is one that I mostly use, is a CHAR array, which is located not far away from where you are, on the Mount Wilson, California. So it's an array of 6 telescopes, which are located in a Y shape, as you can see here, to here, to here, and here. The biggest baseline is of 300 meters large, so they are pretty large baselines, and the smallest is 30 meters large. There is also an interferometer in Australia. There is another one not far away, either in Flagstaff, in Arizona, and also, of course, one in the VLTI. For example, there is Matisse, the new instrument. We choose UTs and the 80s to do observation, and I think the biggest baseline for the VLTI is 130 meters. Why is it important? For a classical telescope, the angular resolution that you will have, which is actually how much you can resolve an object that you are observing. This angular resolution is proportional to the wavelength over the diameter of the telescope. So now the biggest is about 10 meters large. So the angular resolution isn't that big, but you can observe faint objects because you will receive a lot of photons on your telescope. For an interferometer, you need several telescopes, at least 2, and you will recombine the light coming from the telescopes, which will make interference fringes. And the angular resolution, in this case, is not equal to the diameter of one telescope, but to the distance between the 2 telescopes. So the biggest baseline, the best angular resolution. So the good thing is that you can really resolve small objects. For example, if you have a binary star, you will be able to see the 2 stars, and maybe with your telescope, you won't be able to see that you have a binary system. But since you receive less light, you won't be able to observe very faint objects. So how to relate that to parameters of stars? For example, if you observe a star, well, the intensity that you receive is a convolution of your object and your PSF. And there is a theorem that says that the intensity will be related to the brightness of your star. If you do the Fourier transform of your intensity, this brings to that. And actually, this Fourier transform is called the complex visibility, which is divided between the phase and the argument, the modulus. And the von Zitternick theorem says that the contrast of your fringes that you get when you do interferometry equals this complex visibility and is the Fourier transform of the surface brightness distribution of the star. So when you measure the contrast of the fringes, you have information about the size of the object that you are watching. And actually, in the case of a uniform disk, if you consider that your star is just a uniform disk, you can say that the visibility that you observe is related to the Bessel function. And this Bessel function has as a parameter the angular diameter of the star. So it's a bit complex, but actually we can simplify it. So if you have a point source, so an object which is not resolved, you will have a contrast equals to 1. So this is the visibility here, and the spatial frequency, which is related to the distance between the 2 telescopes, so to the baseline. So an object not resolved will give a contrast of 1. So you cannot say anything about your object. Then you will stretch your baseline, take one a bit bigger, and you will start having a different contrast between the that you measure. It will not be equal to 1 anymore. So you will be able to start seeing that your object is not just a point source. So you stretch a little bit more your baseline, and so on. And you will have many visibilities according to your spatial frequency. And then you can say if your object, your star here, is resolved or not. And you can fit your visibility with a model. For example, a new uniform disk model or lambda-darkened model. And this will give you your angular diameter. So of course, if you have a very small star, it will be more difficult to resolve it. Maybe you won't have a baseline large enough to be able to measure a contrast different than 1. But for many stars, actually, we can measure a contrast different from 1. So here is an example of the baseline that you can find on the Chara array. There are the 15 baselines using the 6 telescopes that are here. And this is an example of all the visibility that you will be able to measure within a few hours using 4 telescopes. So it's represented when there are these small sticks here, and it's a representation in 2D. So this is really the complex visibility, and in black here, it's 0 visibility. And when you put it in 1D, it looks like this. So those are all your data points measured with the interferometer. So I said that you can use several kinds of model to fit your data. If you consider that your star is just a uniform disk, it means that you consider that the intensity of your disk is just 1 and then drops suddenly to 0. So it's not really realistic. So there are people who work on that to convert what we measure to at least a lambda-darkened disk. It's difficult because it's something that is very difficult to measure. Actually, it has been done for a few stars, but very well resolved stars. Actually, if you want to measure the lambda-darkened diameter, you need to go beyond the first 0 of your visibility. So this can happen only for very, very big stars. And the problem is that there are discrepancies between the lambda-darkened diameter that we can measure with interferometry and the one that we can infer from the transit measurements, because during the transit you also have to consider the lambda-darkened diameter, and of course it impacts your final radius. So now we know how interferometry works and how Gaia interferes here. So interferometer measures the angular diameter of stars, and with a very easy trigonometric exercise, you can see that with the distance you get the stellar radius. So this is what the equation that we usually use in interferometry, just to accommodate with unities. But you have here an interferometric angular diameter directly measured with an interferometer and the Gaia distance. And here is an example of the visibility that were measured for this star, which is actually 55 Cancri, famous stars which host several exoplanets, among which one is transiting. So we can have the radius if we have a distance. Before we have the Hipparcos, now we use Gaia. But also the angular diameter is used to derive the effective temperature of stars. And for this, we'll need the SED of a star. And for this, you need a model to interpret it. But once you have the bolometric flux and your interferometric angular diameter, you have the effective temperature of stars. So this has already been explained this morning. But just out of curiosity, I checked the photometry of Coro 9, and I find these dots for Gaia. And I was a bit surprised to see that they are very different from the previous photometry from different instruments. So something very strong is to combine transits and interferometry. Why? So if you combine the transit duration and the third Kepler law, if you have an exoplanet which transits, you can measure the stellar density. given this formula. Actually, it's not very complicated. I invite you to do it. It's a very easy computation. So with a transit, you can have the stellar radius. With interferometry, you have the radius of the star, which means that you have the mass of the star. And as was said this morning, it's really difficult to have the mass of a star. There is no way, except in special cases, where you can have a direct measurement of the star. So here it's really linked to dynamics and the interferometry. So I would say that it's a direct measurement. And it's very useful because we can use this mass to calibrate models, for example, for some of stars. So now we can, I will show you two examples of how we use this direct determination of the radius and the masses to determine how some systems are made of. I mean, how they were made and what is the composition of their exoplanets. So instead of taking the parameters independently, we can calculate the probability density function of the radius and the density, and the analytic joint PDF of the mass and the radius, which looks like this. And this will give us a probability of having a certain density. So here, for example, you have the radius of the star 55 Cancri, and here you have the mass. And here is the probability of the density. And actually, in this case, the correlation is high, as you see that the ellipse is very inclined. And the mass that we found is quite different from what was inferred using isochrones previously. And actually, if you take the radius and the density independently, you will have this kind of ellipse. So this corresponds to the uncertainty on the radius, this one to the uncertainty on the mass. And you see that we have densities that are very, very not likely. This is what we were using actually before, and now we realize that having the density, of course, will narrow the possibilities to having a certain masses. So now we can do the same for the planet. We calculate the PDF of the mass and the radius. So to do this calculation, you need radial velocity measurements because you need these parameters, semi-amplitude k, that you are able to measure with measurements. And you need the transit method, of course, because you need the transit for the density, but also because you need the delta F, which is the ratio of the two radii. So what we got at the first estimate was this ellipse in blue. So for this case, we were using Hipparcos parallax because it was what was available. And you see that the correlation was really low. It was 0.3. So we have a very wide ellipse, and we cannot say much actually on the composition. So we did for 55 Cancri E, which is the planet that transits its star. And we found a density for the planet with a big uncertainty. But after Gaia K, so we had the parallax very more precise, and we also refined HST light curve and better radiality measurements, and all combined gave this ellipse, which you can see is very narrower here in the radius direction. The correlation is much higher, so that the uncertainty on the density is much better. And just for comparison, here is the ellipse of another study where they don't take into account the correlation. So you see that the ellipse is not inclined, but also there are discrepancies between the possible densities that we found and some densities that they found. So just out of curiosity, we made a small exercise. So here we have the ellipse for the density for the star, radius and mass. If the uncertainty on the transit depth, so the delta F parameter, and the semi-amplitude K were less good, so like the first case we have, this will degrade the correlation. So that's the first case that I showed you. And actually, if you neglect the stellar uncertainties, here is what the ellipse will look like for the planet. So this was also for the planet. So this is what it will look like if no stellar uncertainties. And if the transit depth and the semi-amplitude were known exactly, we will have a very, very narrow ellipse like this. So of course, that's what we are looking for. So now let's move on a little bit. So now we have the density, the mass, the radius for 55 concrete E. So we can infer the internal composition of this planet. We use the model from Caroline Dorn to do that. And we tested the output of the model according to various inputs. So either we only take the original data and the mass of the planet, so I mean very few parameters as inputs. The C model, the C model takes into account a low correlation, while the H model shows a very high correlation, the one we had during the second study, and the A model takes the abundances into account. So usually we take the abundances of the star to put into model of interiors because we don't know the exact abundances of the planet and what remains around the star. So we computed the cumulative distribution function for all those parameters which are in the model. And we could show that the abundances are able to give us the composition of the mantle. But with a correlation, you can say if there is or not a gas layer. And actually, having a strong correlation will allow to rule out some composition. So here, in this case, it's the pure solid composition. So using all this information, we could say that the atmosphere of the star is really thick. It's only on this planet is really thick. It's only 3% of the radius of the planet. So it's not a good target for doing transmission spectroscopy. But the chemistry is not necessarily carbon rich. It could be made more of silicate, for example. And actually combining strong correlation abundances and the basic parameters constrains the best the interior, the structure of the planet. What is interesting is that Gaia will provide stellar abundances in a homogeneous way for millions of stars, including stars that host exoplanets. And this will be very important because, as I just showed you, we need these abundances to use models of interiors of planets. So I will present you another example, which is AG 219134. It's also a star that hosts several planets too. And we were able to measure its angular diameter using the jar array. So we had good measurements of the diameter. And actually, doing all this study brought to the result that the planets are actually smaller than what was previously estimated. So now with our estimates that are presented here for the two exoplanets, we put the star out of the Photon Gap that I mentioned at the beginning. Before this study, I mean, with other studies, those planets are in the elaboration valley. And another thing which is very interesting is that the two planets are supposed to have similar composition. That's what we found. But planet B is more massive than planet C, while it has a lower density. So that's quite interesting. And if you see the ratio of the two densities, actually there are chances that the difference in their density differ more than the density between Venus and Earth. So this has implications for planetary formation. So where does this difference come from? It could come from a different core and mantle ratio. One could have a sea gas envelope, or there could be an enrichment in refractory elements. But actually, we saw that a molten mantle is 25% less dense than a solid one. And actually, that's the hypothesis that we dug, because the chances that the mantle was molten was higher than the other possibilities. But how does this molten mantle come from? That's what we try to investigate. And actually, what could lead to such a melting of the mantle is a tidal heating from the stars. So tidal heat dissipates energy and circularizes the orbit. So that's what is admitted. But this energy source is possible only if the eccentricity is bumped by another planet. And this is actually the case of Io in our solar system. So to check that, we made n-body simulation of the system, and we could verify that the eccentricity of planet B oscillates between 0.05 and 0.037. And actually, this creates a tidal heating 100 times more than Io, so it's very big tidal heating. And there is less tidal heating for planet C, but it's further from the star, so this explains why it doesn't suffer from such a tidal heating. So these n-body simulations show that planet B is excited by the tidal heating, which leads to high eccentricity. And if you assume a dissipation inside this planet equivalent to that of the Earth, which is actually say the most preferred way of considering the system, this suggests that this planet could be at least partially molten, and this explains the difference between the two densities of the two exoplanets while they have the same composition. And if we make a summary of the two systems that I just showed you, we can see that all the uncertainty on the density of the planet, which is a very important parameter, comes from different other stellar parameters. The density and the transit depth can have high uncertainties, for example, for the system of AG219, and in particular for planet B. For the two planets the same, sorry. And now we have new missions on Sky or coming, like TESS, which is on Sky, and Plato, which will be coming in the coming years. And this will partially resolve the problem of the uncertainties on these parameters. On the semi-major axis, on the semi-amplitude, sorry, we have new instruments like Espresso, which also will bring measurements very, very precise. And with for the radius, we have interferometry with new instruments coming, like the Spica-Chara instrument, and Gaia, for which the parallax goes from the milliarc-second to the micro-arc-second, which leads to a very, very precise stellar radius. So we talked about stellar models earlier. And of course, when we compare what we found with direct measurements and what was found with the model, we see some discrepancies, so it's not new. But for the two systems that I showed you, 55.3 and HD219, the differences between the models and the measurement can go up to 14%. So this is really huge. This is another example with a transiting exoplanet where we did the same study. AJ17658. And you see that the uncertainty are within the error bars, but still it's different. And of course, this leads to different planetary structures. So combining interferometry and planetary transit is very powerful. And of course, with its Gaia, we can have the abundances and a very precise radius of the star. We could do the same with the age. This is a study that I like to show because they show different age according to the method they used to derive the age, and you see that there is also a lot of discrepancies. So the inconsistency in the stellar parameters perturbs the exoplanet composition. This was an exercise made by Pio and Haven in 2011. They used a stellar model called Sesam, where there are many possibilities for the radius and the age. So you see here the distributions, and this leads to different radii of Coro-2b. This was the aim of the study. So you see that it's very, very important. Unfortunately, we cannot measure the angular diameters of all stars. That would be really great, but there are relationships that are made to have the angular diameter of the star, even if you cannot measure them. These are called surface brightness color relationships, and they use photometry and are calibrated with interferometry to have an angular diameter of star. So this is an example of what was done previously. There were many SBCRs, and they were not consistent within each other, especially for stars that are not in the main sequence. And happily, there have been recent studies that show that we can have an angular diameter using these SBCRs within 1 or 2% precision if we have a good photometry. So for all the stars that host a transiting exoplanet, but that we cannot measure with interferometry, we can use these SBCRs that are calibrated with interferometry. Okay, and this is actually one of the goals of the SPICA project. So this brings me to my conclusion. So we never say it too much. Stellar parameters are very important for exoplanetary characterizations, and interferometry is very important in this way. It brings a direct measurement of the stellar radius, which combined with the Gaia parallaxes is very precise. So this is mandatory for determining exoplanet radius, but also the other parameters like the mass and the density of the star and the radius. And these parameters, these basic parameters, are incorporated in the stellar models that are used to exoplanet characterization, because we cannot apply the method that I showed you to every system with transiting exoplanets, unfortunately. And of course, we need all these parameters to be incorporated in exoplanet interior models. So with Gaia, we have unprecedented precision on the parallaxes and then the distance. And with new interferometers like SPICA that I mentioned, we will have very, very precise radii with, very precise means 1% precision. So the SPICA instrument is in commissioning actually now on the Chara array. And it will combine the 6 telescopes of the array. And the goal is to make a survey of 1,000 stars. Among them, there is, of course, a big part which is dedicated to exoplanet host stars. Gaia is not useful just for Earth interferometers, but for astrometry. I won't talk about this because it was very well made previously, and for transits, and with the stellar abundances, this has very interesting and important parameters to infer the exoplanetary structures. And I will stop with this. Thank you very much.
Okay, thank you very much, Roxanne. We have time for a few questions, and I encourage in particular early career researchers to ask questions. I think we have one. Let's start in the room. Oh, not on.
Okay, cool. Yeah, thank you for the good talk. I'm wondering, I know a little bit about radio astronomy, and I'm wondering whether your interferometry is similar in that the light needs to be correlated and that you treat it as a wave. Is that true? Sorry, maybe that's a very basic question. I'm just for understanding.
I didn't hear very well. Sorry, but
Sorry,
you spoke about radio interferometry, right?
Does the light need to be correlated, and do you need to treat it as a wave rather than a particle in order to, like, it's not exactly photons that you're measuring, right? If it's interferometry, you're treating the light as a wave. Is that correct?
Yes, I mean it's electromagnetic waves, and what we get is a fringes. So it's photon actually. Using the Vega interferometer, for example, we had a representation of the photons hitting the detector, for example. I don't know if you answer your question. But what is important is that you need the fringes. So when you have the fringes, you can measure your contrast, you can measure your phase, and that's the important thing in optical interferometry. For radio interferometry, it's a bit different.
Thank you.
Okay, we'll take one question from Slack. So there's a question about does your planetary interior model also affect the atmospheric composition of 55 Cancri E in your simulation for surface exchange? And the second part is the recycled atmospheric composition also taken into account? So I think this is about basically exchange between the interior and the atmosphere in the 55 Cancri model.
I'm not sure to be able to answer this question. It's a model of Caroline Dorn, working at Zurich, who is using, I mean, her model. I don't think that the models goes in such detail. It's already difficult just to infer the composition. So inferring the exchange between atmosphere and the mantle, for example, is I think a step forward.
Okay, and I think we have one more question in the room. Jingwen.
Hi, thanks for the very nice talk. I have a basic question of Chara. So what's the angular resolution Chara can achieve now, and how many stars you can resolve with it so far?
So the angular resolution, the best one that you can achieve is 0.2 milliarcsecond, about that. So how many stars? Well, it depends on which kind of star you want to observe. But if you speak about transiting host star, I mean a star that hosts a planet that transits, I think there are 5 or 6 for now. But it's mostly because of the limiting magnitude. And with Spica, for example, we'll go 1 or 2 magnitudes higher, so we'll go to tens of systems. So hopefully, but this is the goal.
More the better, for sure. Okay, yeah. I think it's time to move on. Let's thank Roxanne again.